Alright, hello everybody. So today we're talking about the integral test, and the idea here is actually computing the sum of series i.e. finding a formula for Sn is hard, so we use various tests to determine convergence and divergence. Right, so as we saw earlier, sometimes finding that formula for Sn is very hard. So let's just consider the series sum from n equals 1 to infinity of 1 over n squared, which is going to be 1 plus a fourth plus a ninth plus a 16th and so on. Right, so let's just look at this series and the function f of x equals 1 over x squared. Right, so you see here, if you just turn this n into an x, that's the function that we have. So let's just graph this function here. So if I draw a graph of this function, this is what it's going to look like. And so I'll draw the graph in blue. You know, the graph is going to look something like this. And let's just draw some markers. So this is 1. Let's say that this is 1. Drew this a little bit wrong, but this, let's say this is 1, and this is 2, 3, and 4. Right, so if we want to find the area under the graph, we can approximate it using these Riemann sums. And if we draw the rectangles for the Riemann sum, then this is approximately what we get. And if we look at the area of this rectangle, the area is 1. Here the area is going to be, so the height of the rectangle, which we said is 1 over x squared. So the height is 1 over 2 squared times the length, which is 1. So this has area 1 over 2 squared. This is going to have area 1 over 3 squared, 1 over 4 squared, and so on. So if we add together all of these areas of the red boxes, then we actually get the same thing as this series here. So just looking at these red boxes, we'd say, well, if we took the integral of this function, we know that that's going to be the area under the curve, which is actually bigger than the area of the red boxes. And we said the area of the red boxes, if we add them all together, is the series. So what I can say here is the sum of the areas of the rectangles is, so remember we have 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus and so on is equal to the sum from n equals 1 to infinity of 1 over n squared. Right, so if we just add together all the areas of the red boxes, that's what we get. And let's say here, excluding the area of the first rectangle, the first rectangle, we see that so we're going to have, so if we get rid of this first rectangle, we're going to have 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on. Right, so if we get rid of this first rectangle, notice here, if we look at the area under the function, that's the integral. So the area under the blue graph is going to be the integral from 1 to infinity of this function, and we know that the area of the red boxes is smaller than that. So this is less than the integral from 1 to infinity of 1 over x squared dx. Okay, so remember here, the reason we have this is the area under the curve. Of f from from 1 to infinity. Okay. So I'll say here, but we know from, so this will be section, so this is when we talked about improper integrals. So we know from when we talked about improper integrals that the integral from 1 to infinity of 1 over x squared dx is going to be equal to actually 1, right? So we figured that out. So this area is equal to 1. So if we add together 1 plus 1 over 2 squared plus 1 over 3 squared plus and so on, then this is the sum that we were looking for from n equals 1 to infinity of 1 over n squared. And, well, we know that this part of the sum is less than 1, and this is 1, so we just added 1 to this thing that's less than the integral. So we can say that this is actually less than 2, right? Because the second part is less than the integral, which is equal to 1, and this first part is just 1. So if we add the two together, we get that this is less than 2, and if we add together all the terms and we get a number that's, if we get a finite number is what I'm saying, so we get a finite number, this means, which means the series converges. Right. So the whole idea of this section is we take these weird sums that we're trying to figure out. This looks like a very hard problem, but we just look at the sum and say, well, if we just take the area under the blue graph, the function 1 over x squared, then that's actually an upper bound for what this number can be. So we're relating this sum to actually the integral of this function. That's the idea of this section. So let me flip over to the next board. So the whole idea of this section is the integral test. Okay, so the integral test says, and these are important, suppose f is a continuous positive decreasing and I'll go ahead and put this one in asterisk because I'll come back to this in a second. But let's say that it's a continuous positive decreasing function on the interval from 1 to infinity, and let an equal f of n. Right, so this is our sequence. We say let the nth term of the sequence be whatever our function is of n. Okay. Then we can say part 1 is going to say if the integral from 1 to infinity of f of x dx is convergent, then you can guess what this is going to mean about the sum. This is going to mean then the sum from n equals 1 to infinity of an is convergent. Right, so this is very useful, right? Because if we can prove that our integral is convergent, then all of a sudden we know what to say about our series. We can say it's convergent. So step 2 is going to say if the integral from 1 to infinity of f of x dx is divergent, then the sum from n equals 1 to infinity of an is divergent. Okay. So notice here this is a very powerful theorem because a lot of the times we'll be trying to find the sum where actually we're trying to find the sum where this is a very nice function that we actually know how to integrate. We have a lot of techniques for evaluating integrals. So if we can actually take the integral of this part here, where we replace the n with an x, then we can just say exactly whether our sum is either convergent or divergent. So it's very useful. And I'll just make one note here. So I put asterisks around the word decreasing, and the reason I did that is here it is not required that f be always decreasing. We only need f to be ultimately decreasing and what that means, so that means decreasing for all x past some x value capital N. Right? So what I'm saying here is if you can pick some number, some entry in the sequence, let's say after the 1000th term in the sequence, everything after that, the sequence is decreasing, then we'd call it ultimately decreasing, right? You just pick some point in the sequence, and after that point, everything after that is decreasing, then we say it's ultimately decreasing. So we don't care about the first however many terms, but if at some point it just starts decreasing forever, that's what we care about. So that's when we would call it ultimately decreasing. Okay. And this is going to come up later in an example that we did. So let's first do example 1. Test the series the sum from n equals 1 to infinity of 1 over n squared plus 1 for convergence or divergence. Right, so what we said here is if we have this nice integrable function, then we can just try to take the integral of this function. So that's what we'll do. So I'll say here, actually, we have a few more hypotheses that we need to validate. So to use the integral test, we must first verify that. So we need to look at the integral test and figure out what we need to verify. We need to make sure it's continuous, positive, and ultimately decreasing. So our first question is f continuous on the interval from 1 to infinity? Right? So this is a polynomial, and why did I say that? This is a rational function. Rational functions are discontinuous exactly when the denominator is 0. But here, this denominator is never 0 since this n squared term is always positive. So we can say here that yes, since f is continuous everywhere. Okay, so our second question here, question number 2, is f positive on the interval from 1 to infinity? Right, so you can pause here and think about each of these questions yourself, but, well, if you plug in any value of n here between 1 and infinity, well, this is going to be a positive number. So your answer is yes. So f of x is greater than 0 for all values of x. Okay, and now our third and final question here to check that we can use the integral test is f ultimately decreasing? Right, and this one is the thing that might be a little bit tedious to check. But the way we check if a function is decreasing, think back to calculus 1. How did we check whether a function is decreasing? Well, we said if a function is increasing or decreasing, that's actually a statement about its derivative. If it's increasing, the derivative is positive, and it's decreasing exactly when the derivative is negative. So it is decreasing on the interval from 1 to infinity if f prime of x is negative or less than 0 for all x greater than or equal to 1. Okay, so now what this says here is we just need to test the derivative. So we need to test f prime of x. So notice here, f of x is 1 over x squared plus 1, but we can rewrite that as x squared plus 1 to the power of negative 1, and now we can take our derivative. So if we take our derivative of that function, remember what we have to do to use the chain rule, we need to take out the power, so the negative 1, multiply it by the inside function to the power of, well, we reduce this number by 1, so this becomes a negative 2. And then now we multiply by the derivative of the inside. So x squared plus 1, the derivative of that. Okay, so the derivative of that is 2x, so we can rewrite this as negative 2x over x squared plus 1 squared. So this 2x became the numerator, and since this exponent is negative, we can pull this part into the denominator and rewrite it in this way. And we're asking the question if this is negative for all x's in this region. Well, here x is a positive number, so if you plug in a positive number for x here, you see that this is actually positive. Why did I say that? This is actually negative is what I meant to say. if you plug in a positive number. So this is negative for all x greater than or equal to 1. So that's what we wanted to check. So we took the derivative, we found it's negative, and that tells us that our function is decreasing. So after you do all of that, that's very important to do to make sure this test even makes sense. But if you do all of that, you can actually use the integral test. So that's what we'll do here. So I'm going to erase it here, but notice what it says is if our integral is convergent, then the series is convergent. If the integral is divergent, then the series is divergent. So that's what we're going to use. So I'll write here, now we can use the integral test. Now that we've verified all of those things, and now we can say that the integral from 1 to infinity of 1 over x squared plus 1 dx, now we need to take this integral. Okay, so thinking about how to do this, remember when we talked about improper integrals, we need to replace this infinity symbol with a t. So we'll replace that with the limit as t goes to infinity of the integral from 1 to t of 1 over x squared plus 1 dx. Okay. And if you remember here, actually this fraction here is the antiderivative of tangent inverse of x. So we can write this as the limit as t approaches infinity of tangent inverse x evaluated from 1 to t. Okay, so this is the limit as t goes to infinity of tangent, I'm gonna start writing that. Tangent inverse of t minus tangent tangent inverse of 1. Okay. Now we just have to look at what tangent inverse of 1 is going to be, and also what tangent inverse of infinity would be. Okay. So now we think about that and we'd say, well, tangent inverse of 1, we just think about what angle gives us a tangent value of 1. And that angle would be pi over 4, right? Because tangent is sine over cosine, and at pi over 4, the sine and cosine are equal, so sine over cosine gives you 1. So that would be the answer there. And now we're looking at when tangent is going towards infinity. So remember, tangent x equals sine x over cosine x. So you're looking for, if this fraction is going towards infinity, then sine of x is getting really large, and cosine of x has to be getting very close to 0. So you look at what what angle gives you that, and if you look at the unit circle, if you look at our unit circle here, then here, if we look at cosine of x is getting very close to 0, remember tangent inverse is defined in this region here from negative pi over 2 to positive pi over 2. If cosine x is getting really close to 0 and sine x is getting really close to 1, then let me actually use a different color here. You're going to have an angle that looks something like this. You're going to get very, very close to pi over 2, because what's happening is your sine is getting larger, but your cosine is getting smaller and smaller, but dividing by that small number, gives you a very large number. So the answer here would actually be pi over 2. Right. So we can actually figure out exactly what that is. So pi over 2 minus pi over 4, that's going to give us our final answer of pi over 4. Okay. So just doing that little bit of analysis, we're able to figure out our final answer. And since the integral of this is equal to pi over 4, we know this sum is actually less than or equal to the integral. So we know the sum is actually less than or equal to pi over 4. So I'll say here, since the integral from 1 to infinity of 1 over x squared plus 1 dx converges, right, we said it converges because it's equal to some number. We're going to have that the sum from n equals 1 to infinity of 1 over n squared plus 1 converges by the integral test. Right, so just think back what we did in this problem. First, we validated that our function is continuous, positive, and ultimately decreasing. Second was we took the integral of our function from 1 to infinity, and we said we got this number, and this number is actually going to be bigger than or equal to the value of the sum. So this sum is at most pi over 4, and since that's true, it actually converges by the integral test. Okay. So we can also say, let me just use a new page here actually. There we go. Right. So we can ask the question, when do we actually use our integral test? So I'll say here, when to use. The time when we use it is use the integral test test when you know how to integrate the function. Right, so anytime we know how to integrate the function and we can validate the three hypotheses that our function is continuous, positive, and ultimately decreasing, then we can use our integral test. Okay, so the next thing here is talking about a p-series. And I'll say here a p-series is a series of the form the sum from n equals 1 to infinity of 1 over n to the power of p. So if you have a series of this form, it's called a p-series. And let's just draw some examples. So examples, let's say we had the sum of n equals 1 to infinity of 1 over n squared. Then as we saw, we can use the integral test to prove that this function is, that this sum is actually convergent. So I'll say here that this is convergent by the integral test. Right, because if we take the integral of this, remember, if we take the integral of 1 over x to the p, if p is greater than or equal to 1, then this thing is going to be convergent. Just greater than 1. If it's equal to 1, it's divergent. So if this value here, this 2, is greater than 1, it's convergent. Okay. Next example, sum from n equals 1 to infinity of 1 over n. So remember, again, we use the integral test. We'd say when we're taking the integral from 1 to infinity of 1 over x, we again used what we knew earlier and said, well, that integral was divergent because power on x is less than or equal to 1. So this is divergent. And our final one that I'm going to write here is the sum from n equals 1 to infinity of 1 over the square root of n, which is the same thing as the sum from n equals 1 to infinity of 1 over n to the 1/2 power. Right, so we again look at the power, we say that's less than 1. So using, again, our integral test and using the fact that the integral of 1 over x to the 1/2, well, this 1/2 is less than 1. We know the integral is divergent, therefore, using the integral test, we know that the series is divergent. Okay, so we can write a theorem, which looks very similar to what we said for the integrals. Our theorem is going to say, if p is greater than 1, then the sum from n equals 1 to infinity of 1 over n to the power of p is convergent. Okay. And similarly, if p is less than or equal to 1, then the sum from n equals 1 to infinity of 1 over n to the p is divergent. So again, you can validate both of these using the integral test. Okay. The next thing I'll write down actually, have I used the other side? Yes, I have. Okay. Okay, so note the integral test does not tell us the sum of the series. Remember, so the last integral we did, we got pi over 4. That wasn't actually the sum of the series, we just knew that the sum of the series was less than that number. So, I'll say here we saw that the sum from n equals 1 to infinity of 1 over n squared was less than 2. But we don't know the actual sum. So actually, in fact, we know that the sum from n equals 1 to infinity of 1 over n squared is going to be actually pi squared over 6. But we can't figure that out from the integral test because the integral test just gives us an upper bound. So it just tells us that it's less than 2. And if you computed this number, this is less than 2, but it didn't tell us that it was exactly this number. So it just tells us whether something is convergent or divergent. That's all it tells us. So let's write out the final example for today. Example number 2 is going to be determine whether sum from n equals 1 to infinity of natural log of n over n converges or diverges. Okay. So the first thing to ask is whether it's a positive function and whether it's a continuous function when n is greater than or equal to 1. And in fact, you can check this, but we can say here that f of x equals natural log of x over x is positive and continuous when x is greater than or equal to 1. And then our final question there is, what about decreasing? Right, so we need to figure out whether our function is decreasing. So again, we said the way we check this is by taking the derivative and seeing whether it's positive or negative. So again, we need to take our derivative. So f prime of x is going to be equal to, so remember the way we take our derivative here of this function is by using the quotient rule. So I'd encourage you to try to do this on your own. But when we use the quotient rule here, the way we do it is, let's actually say over here, if we have that's not what I meant to write. If we have a top function over a bottom function, then the way we take the derivative here was by taking the bottom function times the derivative of the top function minus the derivative of the bottom function times the top function over the bottom function squared. Right? So that's how we take our derivative. So we do the same thing here. So the bottom function, which is x, times the derivative of the top function minus the derivative of the bottom function times the top function over bottom function squared. So that's how we take our derivative. Now we just take our derivatives on the inside here. So we've got x times 1 over x minus natural log of x over x squared, which is 1 minus natural log of x over x squared. Okay. And now we're trying to figure out when this value is negative. So I'll say here, this is negative. Well, we can ask when our fraction is negative. Denominator is never negative. So it's negative when the numerator, 1 minus natural log of x, is actually negative. But that means that that 1 is less than the natural log of x. And we have to look at when that's true. Well, when do you get natural log of x is equal to 1? Well, remember, natural log of x is saying e to what power gives me this number. That's going to be the power there. So e to what power gives me 1? Well, here, e to the power of, oh, I said that the wrong way around, sorry. E to this power gives us x. So e to the first power would give us 1. Sorry, messed up the explanation there a little bit. But saying e to this power gives us x, so e to the power of 1, that should be x. So x is 1. Or sorry, x is e. That's what I meant to say. So this is, again, log base e of x, so e to the power of 1, that gives us x. So x is e. So, jumbled the explanation a little bit there, but I'll say here that 1 is less than natural log of x for all x greater than e. So, what can we say here? Pause the video and think what we can say here. But what we can say here is, well, at some point the sequence is going to start decreasing, right? Because the derivative is going to start being negative whenever this x is bigger than e. So we can say f is ultimately decreasing. Right, so as long as this x is bigger than e, then it's going to start decreasing. Okay, so now that we know that our function is continuous, positive, and ultimately decreasing, that means we can actually use our integral test. Right, so these hypotheses are very important to check, because if you don't check them and something actually fails one of the hypotheses, then you can get an answer that actually doesn't make sense or is just completely wrong by using the integral test. So that's why you always have to be careful about what the hypotheses are. But what we can see here is then the integral from 1 to infinity of natural log of x over x dx is going to be equal to the limit as t goes to infinity of the integral from 1 to t of natural log of x over x dx. Remember, we just replace that infinity with a t. And now we need to take our antiderivative, and here we're going to use u substitution. So we're going to use u substitution with u equals, so pause the video here, think about how you're going to use u substitution here. But here you need u equals natural log of x, so du is 1 over x dx. So if we do that, then we're going to get the limit, and I'll do this without changing the limits. So if you do this without changing the limits, then we're going to get the limit as t goes to infinity of the integral from x equals 1. Remember, there's two different ways of doing this. I'm just going to do it this way to show you how it works. So we're going to get the limit from x equals, the integral from x equals 1 to x equals t of the numerator was u, and this 1 over x dx became du. So now we take our integral, we're going to get the limit as t goes to infinity of u squared over 2 from x equals 1 to x equals t. But remember, this is from x equals 1 to x equals t, so we need to replace what u was. If we change the limits, we don't need to replace what u was, but here we do need to replace what u was because we didn't change the limits. So it's the limit as t goes to infinity of the natural log of x squared over 2 from 1 to t. And now we just plug those in. So we're going to get the limit as t goes to infinity of natural log of t squared over 2 minus natural log of 1 squared over 2. Okay. So now we can say here, e to what power gives me what's on the inside here. So e to what power gives me infinity? Well, your answer there is infinity. And here, e to what power gives me 1? Well, that's going to be 0. So we're going to get infinity minus 0, which is going to be infinity. So now you can ask the question, what do we do from here? Well, remember, if this integral is divergent, then the integral test tells us that our series is also divergent. So I'll say here, since the integral from 1 to infinity of natural log of x over x dx diverges the sum from n equals 1 to infinity of natural log of n over n diverges by the integral test. And that'll be your answer there.